So continuing on with my motor drive design, in this video I will be continuing to review the ICs on the circuit and looking at all the pinouts, making sure that the packages are correct, making sure that the footprints are correct, and just going over the list, the remainder of this list. I don't have that many components, but on the other hand, many of them have a lot of pins, so it's going to take some time. But I just want to revisit this op-amp circuit here. In the last video that I have been looking at these resistors, and I thought, well, what if signal from here goes through here and ends up here? But I think, yeah, so I simulated this in LT-Spice, and it looked like there will be a little bit of noise because of this interference, but it's very minimal. It's like in the order of millivolts. I think what I got here. Oh, I closed the LT-Spice. Okay. Anyway, so the reason I think that this works and does not really couple the noise so much from this input to this one is that the output impedance of this of any op-amp is usually very low. In this particular case, it's 2 ohms, and so this means that the op-amp is a very good voltage source, and when there is current flowing here, the current is very, very small, and what the op-amp does is basically, if the voltage rises here, because this is the reference voltage, this is supposed to be somewhere in the middle. It doesn't have to be perfect. It just needs to be a small reference voltage to offset these signals from 0 point to the midpoint. What basically happens here is that the op-amp is able to regulate the offset voltage sufficiently to keep this noise very small. So if this works the same way as it did in the simulation, then I think this is going to work fine. This circuit is, by the way, from the application note that I found from I think it was TI, which described amplification of the back EMF in order to be able to sense back EMF when the back EMF is very small. So I'm going to be evaluating this circuit. I don't know how well it's going to work, but it's an interesting circuit that I want to test, and I want to see if this is able to provide better results than just sensing the voltage directly. So moving on with my list here. Next on the list is the stm32, and I've chosen stm32F429ZET6, which comes in a 144 pin package. Let's see. Which comes in a 144 pin package, and let's look at this STM32 on Mouser. So I'm going to close this. Right, and also just before we move on, I think what I also looked at was how much current can this op-amp sink on the output, and we are well within the range because we have a 10K resistor there, so any current that flows through that circuit and into the op-amp is going to be very, very small. Anyway, I'm going to close this datasheet, and I'm going to move on to STM32. And obviously, if you think that anything I say is wrong, then just feel free to comment on the video, because sometimes I can miss things, I can maybe misinterpret something, and it's very important that you point it out. So please do that in the comments. Let's see. I'm going to open this chip, and I'm going to first check that it's 144 pin package based on this article code. And then I'm going to go through the data sheet and look at every single pin. Come on. There we go. All right. Let's see what the difference is here. So we have ZET6 TR, which is a new chip, LQFP144, by the way. But what is the difference here? I guess that will be more apparent from the datasheet. Let's open the datasheet. And I'm curious to look this up first. What does the TR mean at the end? So I'm gonna, let's see. Where is the table of contents? No table of contents? Total sidebar. Okay. No table of contents, but we have a sidebar. So that's next best to a table of contents. Let's see if this table of contents works. Okay. Where is, let's see. They have, somewhere at the end of the datasheet, I think they have the description of the article codes. So part numbering, there we go. Awesome. So ZIT6, right. T6 means industrial range minus 4285. T means LQFP, and then we have TR tape and reel. Okay. It was as simple as that. So this is just the packaging of the chips themselves. So it's the same component here. It's just that this one is delivered as a tape and reel, and this one is delivered as single chips, sort of packaged between like plates of bubble wrap, or like, yeah, whatever. This is just the packaging of the chips themselves. So moving on to the pins, I'm gonna go back to this. Let's see if I can find the pins directly. There's a table of all the pins, and it's supposed to be somewhere here, I think. But without a table of contents that's easily available, it's getting a little harder. So we have the pin out here. This is LQFP 100. This one is LQFP 144. Okay, so instead of looking at the package itself, I'm gonna look at the table of the pins, so I can just double check that every single pin that I've connected has the functionality that I need. Let's see here. So let's look at the schematic, and I think that a good way to review this would be to actually just go through the pins here instead of making any pin tables and stuff like that. So I'm just gonna check that this is a LQFP 144, which it is, 2020, and pin 1 is connected to UX clock. So this is supposed to be, so pin 1 is supposed to have SPI 4 clock, which means that we can also make a note here that, let's see what notes we have here. We can move this for now to this side here. And I'm going to add a little more text here. So we have, let's see, let's copy this. No? Duplicate. Let's see. SPI4 is UX. Let's see, SPI1, SPI2, SPI3. And now we can just look at the pins. So pin number 2. Pin number 2 is connected to UX power enable, which means that we're going to be using the GPIO PE3. And pin name, function of a reset. Okay, yeah. So we're going to be configuring this as a GPIO, and that seems to be fine. Pin 3, UXCS is also a GPIO. Pin 4 is MISO, UX, so SPI 4 MISO, pin 4. We have SPI 4 MISO here, that's correct. Pin 5 is UX MOSI, so we have SPI 4 MOSI. Pin 6 is, let's see, where's pin 6? Pin 6 is right nowhere to be found. Where's pin 6? Maybe pin 6, does pin 6 even exist? Oh, that's the VBAT pin. Okay. Yeah, pin 6 is the VBAT, and it has it's connected to VDD33 MCU and has a bypass capacitor. Pin 7 is pin 7. I think I saw pin 7 somewhere here. Let's see. Pin 7 is PC13, 8 and 9. We have them unconnected. So PC13, 14, 15. Pin, let's see, we have LQP144, so it's the second column there. So pin 10, let's see, yeah, okay. Pin 10 is, let's see where pin 10 is. Pin 10 is UXSDA, which is then I2C2. So we can add another text here, and let's see. And this would be I2C1, I2C2. UX, and let's see, pin 11 is SCL, which is here, UX SCL. Pin 12 is analog input power enable, so it's going to be, pin 12 is, let's see, where's pin 12? There. This is going to be a PF2 GPIO, and pin 13 is VMOT sensing. So pin 13 would be configured as ADC3 in 9. We need ADC3. VMOT, so okay. Next is, let's see, pin 14 is potentiometer multiplexer, which would be right. Pin 14 is for sensing the potentiometers, so to be connected to IDC3 in 14. Let's see. ADC3 channel 12, channel 13. So let's also double check with this. Let's see. So 14 would be the potentiometers, and 15 would be AC315. Let's see. AC3 channel 15. That will be temp not 1. And pin 21 is external GPIO int A. Now, pin 15, pin 16. What was pin 16? That was one of the grounds. Pin 16 there. Okay. Pin 17 then is a VDD pin. Yeah. And then pin 18 is PWM input, which goes to TIM10 channel 1. So pin 18 is TIM10 channel 1. Let's see. TIM10 is PWM1. And TIM11 is pin 19, TIM11 channel 1. So TIM11 channel 1 would be, TIM11 is PWM2, and we have pin 20 is supposed to be connected to ADC, I would guess ADC3 in 6. So we have ADC3 channel 6 would be the temperature, let's see, temp not 2. And then we have pin 21, which is GPX. So that would be PF9 as a GPIO. And it's important to look what the pin function is after reset, because if we have something that is something different after reset than what we expect, then things may not work correctly. So we have PF9, that will be GPX int A, and GPX int B would be on PF10, pin 22. Next is, okay, then next one is 49 there. So next is here pin 23, which is oscillator input, which I suppose would be here, pin 23 and 24, and oscillator output. And reset is pin 25. Pin 26 is PC0. What the hell just happened? So, there we go. PC0. Let's see. So let's do a little bit of reviewing here. So 26, 27, 28, 29. 4 of these are going to be right. So let's see, PC0. So this would be voltage sensing, but I just want to make sure that that we have, let's see. And 11 and 12. Yeah. I think that just for the sake of keeping things in a little bit better order here, I'm just gonna swap places on these pins, because then I have voltage sensing for the A phase is on input 10, and then the B and C phase come to input 11 and 12. And the same thing here, so that we have a bit of an order here. Makes better sense. I think my original placement was pretty much arbitrary, and it's possible that I may change some pinouts later when I do the layout, but for now I'm gonna make them oh, actually, of course, this one is supposed to be, let's see, like this, and VSA2 is gonna be there. Okay, then we have ABC, ABC. So 10, 11, 12, and 13, 14, and 15. Let's see what we can do here. So the way that stm32 ADC works, I think, is it can sample on all ADCs at once. So it can sample sort of channel 1. Let's double check this. It's possible that it can sample channel 1 on ADC1, channel 2 on ADC2, and channel 3 on ADC3 at the same time, or something like that. So I have to go to this reference manual. I'm going to bring up the reference manual. So we can connect the ADC pins correctly. So what we want to ensure here is that, because we have very small time frames to sense the voltage on all of the phases, we want to ensure that we can sense all 3 channels at once. Where is the ADC? Power, RCC. Where is the ADC? There we go. Main features. So VRF minus is basically ground, and VRF plus is 3.3 volts. Let's see. So there is a sampling description somewhere down here. There is some kind of synchronized mode as well. I'll just find where they describe this. Okay. Something else to think about is if we use DMA, we have to make sure that we can allocate the channels in such a way that we have free DMA channels as well to sort of do the job of converting both current and voltage sensing inputs. And I wonder how this will work now if we have two motors and we have to sense. So we have to program the ADC in such a way that we can sense all three channels as quickly as possible, and preferably in parallel. But it doesn't have to be in parallel; it just needs to be as quickly as possible, so that the sampling is done at roughly the same time. So maybe I will assign the ADC inputs of one motor to one ADC, and the ADC sensing from the other motor to a different ADC, so that I can program the ADC precisely, and then maybe do some kind of interleaved sampling or something like that. Let me see here. So so this is parallel mode of sampling. Triple ADC is also possible. The problem that I can think of with this is that if we have the PWM interrupts happening at random, we don't want to start a trigger or to trigger any conversions from both motor 1 and motor 2, because we may run into situations where we cannot do that if a conversion is in progress. So if I only had a single motor, it would be a possible solution. But because I have two motors, I have to think that I need to isolate the resources as much as possible and only access an ADC, preferably from either one or the other, the code that controls either the first or the second motor. So I don't think that triple ADC mode is suitable. But there could be interleaved mode. Okay, yeah. Obviously the ADC cannot convert more than one channel at once. It has to finish one conversion before going to the next conversion. So the way injected channel works, injected channels are designed to be able to have one sequence that is triggered regularly, and then you can have injected sequence where you trigger the injected sequence and it converts, it aborts the current conversion, it converts the injected sequence, and then it continues with the current conversion. So kind of one solution would be to have the channels of the first motor as regular channels, and then the channels of the second motor as injected channels. But there is still, I want to avoid as much resource sharing as possible, because that can lead easily to problems. And I think that the best way to connect these channels is to make sure that we have the option to use either ADC1 or ADC2 or ADC3 even for a particular channel here. So for example, with all the voltage sensing inputs, we can choose between either 1 or 2, and in fact here we can choose 3 as well. So let's look at pin 26. So pin 26 is ADC 1 to 3 in 10. And 11 is VSA not 2. I'm going to put this in parentheses because I want to, or actually, yeah, let's put them in parentheses. So this would be a possible configuration. So we don't want to take this channel for anything else, and I don't think we can do that either, because ADC channels are they're not possible to remap. So let's see. VSA not 1. 13, 14, and 15. So let's see, 29, and then we have 30 is VDD. So let's just review these pins. We have 30 VDD. 31 is VSSA. 32 is VREF plus. Let's see. Yep. 33 is VDDA. 34 is PA0. So we have 34 is HAL A2. Which should be connected to, let's see, the timer. Timer 5, I guess. Yeah, channel 1, and then 35 is channel 2. And channel 3, timer 5, 36. 37 is sensing, let's see, in 3. Let's actually just like this. Car A mod 1, car B mod 1. But channel 6 is not I'm not using channel 6. Let's see. Right, channel 6 is break. So 37 and 40. 37 is in 3. And 38 is VSS. there. 39 is VDD. And 40 is the channel, let's see, in 4. Yeah. So B. Yep. And then 41 encoder A. So 41 has to be connected to that'll be channel 2, timer 2 channel 1. So that's encoder 1. Yeah. And then we have number 42 is motor brake or encoder RQ. So 42 is supposed to be connected to motor 2, which is timer 8 brake input. Correct? 43 is in L. What is in L? Right. Let's see. 43 would be connected to timer 8 channel 1N. So it's important here that let's see, 43. So it's timer 8 channel 1N, and what we need to do is make sure that in LA 2 is channel 1 and in LB 2 is channel 2N, and channel 3N is in LC. And then we have in HA, which will be, let's see here, in HA2 would be channel timer 8 channel 1, 2 and 3 ABC, to make sure that we don't connect these pins wrong or to different timers or something like that. That would be highly unfortunate. So 43, 44 then. Where is pin 44? There. 44 is connected to voltage sensing for motor 2, which is input 14 and input 15. Right. So something that's important to note here is that when we have it like ADC 1 and 2, they share some pins, but then ADC 3 has its channels 14 and 15 on different set of pins. So we can we need to just like this. I don't think this is, let's see here. Right. 14 and 15, and it's just ADC 1 and 2. Yeah. All right. and then we have timer 8, 996. Yeah, we can move that. We can move to these pins later. I'm gonna follow the table here. So we have 44, 45, 46 is PB0. Let's see. PB0 is here. 46 is input 8 and 9. 46 and 47. So that's current sensing for, let's see, yeah, 8 and 9 there. I'll just give them some short names. Yeah, it's possible that I make ADC1 used for motor 1 exclusively, for even for voltage sensing, and ADC2 for motor 2. We'll see. When I start with the software, I'll see what I will do. But for now, I keep it like this. So 48 is the boot one. 48. Where is pin 48? There. Boot 1 connected to ground using a 10K resistor. And I'm just gonna double check the pin configuration for them. Let's see. Yeah, pretty much here. Is the bootloader only on CAN 2? Interesting. Something we need to check here is also, I think PA9 and 10 is pretty safe. Let's see. Yeah, but the other pins, we have to make sure that we don't mess something up here. So we have this one is enabled, PB10 and 11. Let's see, PB10 and 11. So that's gonna like, let's see, PB10. So PB10, I think that the bootloader is pretty much like sleeping, unless you kind of send an activation byte to it. But just to keep in mind that this pin is connected to an output. In this case, it will not matter because, yeah, sure, we may power certain things up if something is sent here, but let's see. And I think actually this will go high if the bootloader is activated, because this would be the output, the transmit pin, which is good to keep in mind, which will power this chip and the encoder interface. But let's see what else we have here. So we have PC10 is output as well. What do we have on PC10? Yeah, clock for the GPIOs. That's fine. Right. Okay. That should be fine as well. CAN2, PB5 and PB13, or PB13 primarily, that's what I'm interested in. So PB13 is connected to CAN, that's fine. PB9, PB6 and PB9, let's see. PB6 is HAL input, PB9 is write enable on the EEPROM. Okay, that should be fine. I don't think toggling the write enable pin is going to be any issue. I don't think so, but if I'm wrong, then feel free to comment on the video. Let's see, so we have I2C2, PF0 and PF1. PF0 and PF1. That's UX. Yeah. But that's actually good because we have this I2C connected to UX connector, which means that we can actually flash this chip over I2C. PA9, PA8 and PC9. PC9 is a test point and PA8 is the diode. Okay, that's fine as well. We have PA7, 7654. Now 7 is okay. We're mostly interested about PA6. Like, we don't want PA6 to be connected into any op-amp output or something like that, because we don't want to have two output pins connected together. PA6 is the break input, and also the interrupt. So this can short to ground, so that's good to keep in mind. Wait a minute, mastering. Yeah, okay, yeah. But wait a minute. This one is supposed to be out, but not this one. How is this even, like, what's the logic here? This master in, slave out. This is supposed to be input. And master out, slave in. This is supposed to be output. Let's see, PA7. Master out, slave in. Okay. So this one will be connected. This one is interesting. This one will be connected to the, let's see, to this current output. And yeah, and because we have the 3K resistor there, that's fine. If they both try to drive this this line, it's gonna be okay. But I think the datasheet is wrong here, or this application note at least. Let's see, PI3 and PI2. So master out slave in would be PI3, which would be the output. Where's PI3? Let's see. I don't think we have a PI. We don't have the PI port. But PE14 is something we could have a look at. That's an interrupt. PE14. The LED interrupt. That should be fine. That's an open collector. That will kind of pull the line low, but I don't think it shouldn't do that under normal circumstances without anything being sent to the chip. So the chip will be uninitialized at this point, so that should be fine. 429, let's see. Now for some reason this PDF document just jumped. Right, and then we have the DFU is PA11, PA12, which I think is connected to the USB. Yeah, 11 and 12. That's good. All right. So this was a good thing to check. This is not always obvious, that if you put the chip into boot mode, you can actually have a situation where the chip tries to drive some pin that you also drive externally. Let's see. Yeah, so what I was looking for were the boot patterns, because I was going over the boot pin. I think they're the same for all chips, so we can probably just look at this diagram here. Yeah, so we are interested in booting from system memory. That would be the bootloader that is in the ROM. Which means boot 1 is supposed to be 0, and we just pull the boot 0 high. So that's checked. That means that we have pin 48 is checked. And I'm going to go to, let's see, I'm going to go to the reference manual. Or rather the data sheet, not the reference manual. So pin 48, pin 49 is PF11. Let's see what we have on PF11. That's a GPIO pin. So this will be just a normal GPIO. PF12. Motor over current input. This would be an interrupt input, and all GPIOs on stm32 are capable of detecting interrupts or detecting pin changes, so we can green light that one as well. 51 is VSS, and 52 is VDD there, 51 is here, 53 is PF13. 53, 54, 55. These ones are, so let's see. The gain output will be either high or low, so this would be a GPI connected as output. Basically, yeah, basically all of these pins are, let's see, they're connected as GPIOs. 56, PG0. GPI reset. 57, GPI int, and 58. Is PE7. Button LEDs enable, going to be also GPIO. 59 is PE8. So low input for the A phase on motor 1, which is low ones are the inverted ones. So it's team 1 channel 1, 59. And 60 is team 1 channel 1, which would be the high for 1, and 61 is VSS, and 62 is VDD. Yep. And 63 is so that will be in B and low, because it's the inverted one, and high would be on 64, team 1 channel 2. 65 is the low one. Let's see, 65 is the low one, which goes to PE12, channel 1, channel 3, and 66 is channel 3, is the high one for the C phase. 67 is connected to button LED interrupt. 68 is encoder interrupt, which is also the break input. So 68 is supposed to be connected to team 1 break, which is correct. 69 PB10. Right, so I may change, let's see, god damn it, come on. '69 there, yeah. Let's see. I may change the high and low ordering of these pins. That would depend a little bit on the layout, because if this configuration results in a layout where I have to cross the lines to connect them to the motor driver, then I will have to swap places between H and L, and to make sure that the lines can be just straight and going directly to the motor driver. But we'll see how that turns out. 68, 69 is PB10. That's encoder power enabled for 2. And 70 is that will be the GPI pins. 71 VCAP 1 there. 72 is VDD. 73 is PB12. That's counter X2, so it's supposed to be counter X2, PB12. And the TX is PB13, which is next pin, 74. 75 is connected to teammate channel 2N, which is the B phase, and low one, and 76 is the C, so that will be connected to team 8 channel 3, and 77 77, 78, 79, there would be PD 8, 9, 10, which will be GPIOs, and 80 is PD 11, but then we have 81 is encoder A, which is encoder on motor 2, which would be, so motor 1 is channel 2 and channel timer 1 and timer 2 and timer 3 and timer 1, of course, and then we have encoder on motor 2 is connected to timer 4, channel 1 and 2, so 81 and 82. 81 and 82, and let's see. And ENC-Z is basically GPIO pins. So 85 and 86 are going to be used as GPIO pins. '87 PG2. GPIO 87, 88, 89. CAN standby 1, standby 2, 90, 91, 92, 93, 94, 93. Yeah, so up to 93, which is PG8. Yeah, PG6, 7, 8, 93. 94 is VSS. Yep, 95 is probably VDD. Yep. And 96 is PC6. Let's see here. '96, '97, '98. That's the high A, B, and C for motor 2, which means that's going to be team 8. Team 8, channel 1, channel 2, channel 3. 99 is just a test point. 100 is 100 is the boot pin, I think. No, it's the LED. Yeah. 100 is the GPIO. 101 is UART 1. And 102. So on 102 UART 1 TX/RX. Damn it. Again. I think I have to click on the page to make sure that it doesn't go back when I press like tab or something. Let's see. Let's go select that. So UART 1 TX. God damn it. Why is it jumping? Okay, UART 1 TX is supposed to be on 101. Yeah, TX/RX. 103 is USB 3 and 4. 103 USB OTG FSDM, which is USB N and P. 105 is SVD IO. Let's see. SVD IO. 106, 107, 108. VCAP2, 106, 107 is VSS, and then it's VDD. 108 is the VDD. Yep. 109 then is the clock for the JTAG. SW clock for the JTAG. 110 is GPIO PA15. 111 PC10. SPI3 SCK. Yeah, let's see by the way here. We have SPI3, we have somewhere here. Let's make this. Let's see. So we have SPI3 using GPIO and I wonder what else. Let's see. Yeah, so SPI3 is GPIO and encoder. So shared between GPIO and encoder, and that would be, the clock would be at 11, and then 12 would be MISO, and then MOSI. Let's see if this is correct. Clock, MISO, MOSI for SPI3. 114. CAN RX. CAN 1TX. 16, let's see, 16 is enable gate 2, enable gate 1. 16, 17, 18, 19, up to PD5. All of these are GPIOs. 120, 121. 120 is VSS. 121 is VDD. Great. 122 is PDD. Oh, let's see. 122 is the GPIO and 123 as well. 124 is PG. Let's see. Kind of the interrupt. So 124, 25, and 26 up to PG 11 is GPIOs. And 127 is kind of D and EtherCAT. So MISO, SCK, MOSI. MISO, SCK, MOSI, SPI6. PG 14. 130 VSS and VDD 131. 130, 131. 132 is PG 15. Switch interrupt. So that would be a GPIO. 133. Let's see. That'll be the SVO pin. 133 is used for something else, I think. NB1. So be channel 2 for motor 1, which would be team 2, I think. Team 2, channel 2. 133. 134, ABC 4, 5, 6 for motor 1, which is timer 3. 1, 2, 3. Channel 1, channel 2. 136. So what was the idea here? This is a small mistake actually, I think. Wait. Motor 2 how? No, that's motor 1. Motor 1 how? It's team 3. So actually, we need to have 137 needs to connect to team 3, channel 3. Otherwise, this is not going to work. Wait a minute. LC1. Okay. So, what is timer 4 used for? Okay, that'll be encoder. Channel 3. PC8. PB0 and PC8. PC8 is taking, and PB0 is an ADC channel, right? So this would probably, let's see. ADC 1 and 2. Can we have this somewhere else? Damn, this is really annoying. So we have to move this C. We have to have it here. Unless we can map Team H channel 3 somewhere else, which I don't think we can. I think it's only available on hard pin package. PC8 PH. Yeah. So it's only available on PC8. Channel 3N, but channel 3 is available on PC8. Okay, so this has to go here. But now we have to put this sensing for the current for phase A somewhere else. ADC1. So we have to move from channel 8. Let's see. ADC1 channel 1. So 1, 2, and 3. Let's see. I think ADC is only available on a single pin. So ADC 1, 2, 3. Yeah, that's only on PA1. Yeah, so we can say that because of the HAL sensors, which go to channel, let's see, timer 5, I think. Yeah, and we can't move timer 5, can we? PH is not available. Tin 5, let's see, 5, channel 2 then. PA1 and PH. PA2 and then PH12. Okay. So these ones are not available. But then how can I sense? Oh, okay. So there is actually in 0. ADC in 0, channel 0. Not available. Or what should I put as sort of, yeah, let's put X there. So these ones are not available. Then we have channel 5, 6, and 7. Five is encoder input, which is timer 2, channel 1. Maybe, let's see. PA. So PA0 and PA5. And actually PA15 as well. Yeah. Thank you. So timer 2 channel 1, which we have connected to encoder motor 1, is also available on this pin here, which means that we can move this one out, and we can move this one here, and we can move this one there, and let's see, so that would be on channel 5 instead. So instead of channel 8, move this one to channel 5. And channel 8 is actually taken now, so this would be channel 5. And then we'll paint this one as well. You can see channel 0 is taken. Okay, great. And there is just one pin there, which I think, let's move it to PC9 there. That would be good. Yeah, and then just channel 6 and 7. What do we have on PA 6 and 7? That's the break, and 7 is channel 8, timer 8 channel 1N, which means that 6 and 7 is also unusable for anything else. So I've used up all the channels on these ADCs. The only ADC channels that I may be able to use for anything else is ADC 3. Okay. So which pin was I on? Did I check 120? Let's see. I think I went to 132. Yeah. Hundred 133, 134. Wait, okay. So I think I copied this label actually, which I shouldn't have done. So I was on 136, which was so Team 3 channel 1, channel 2, and then this one was free. So I can move this, let's see, I can then move this pin here, which would bring it slightly away from any of the interference that the switching may cause. Okay, so I can have that there. So I have HAL A, B, and then HAL C is here, which is timer 3, channel 3. Right. $137 is timer, let's see, BB7. That's SDA. IGC1. 138 is boot 0. 139 is SCL. 139. So these ones are, let's see, do we have an IGC here? There. IGC1, the digital potentiometers, the EEPROM, and what else? What was the last thing there? Yeah, and the LED. All right. $140 is EEPROM write enable, which is PB9. 141 PE0. UX. 41 and 42 is UART 8 RX and 8 TX. I think we should copy this and do the same thing for UARTs. So UART 1 is debug. UART I guess this would be UART 8 and UX. Was there anything else? Yeah, I don't think I use UARTs for anything else. So 43 is PDR on and 44 is VDD. And 43 is PDR on, which is connected to 3 supply, which is good. All right, so very, very, very productive. Discovering that HAL sensor misconfiguration was very, very valuable. It would not be possible to use HAL sensors on motor 2 if I didn't discover that. Let's see, 176, this one is probably 144. So one last thing that I'm going to do is I'm just going to check the footprint itself. So 36, 37, 38, and everything looks good here. Yep. And 0.5 millimeters in pitch. Yep. I'll just check the LQFP 44 as well. So 22.6 across, which would be from here to here. Yeah, that's fine. It's a little bit wider because the pins stick out a little bit more, but it's fine from the perspective of being correct. It's just easier to solder. So 1980. Yeah, it's fine as well. Alright, 0.35 is the width of each pin. .30. Yeah, could use a little bit wider pins, but it's very, very small difference there. Okay, so we can greenlight this one, and I'm so happy that I'm finally done with the stm32. That's the largest chip on this board. I can finally greenlight it. And if you think I missed anything, or if you think I did something wrong in this video, then feel free to comment on this video. Until next time.